Welcome to the Global Composites Experts webinar series. My name is Wenbin Yu, Director of the Composite Design and Manufacturing Hub. This webinar series is to examine the history, present capabilities, and future of composites with the goal of sharing the knowledge of composites that has been developed over the past 50 years. This webinar series was initiated by the Composite Manufacturing and Simulation Center at Purdue University. We are located in this beautiful Indiana Manufacturing Institute. All of you are welcome to visit us when life returns to normal and it is safe for us to travel. We launched the CDM Hub in 2013 with the mission to convene and serve the global composite community by creation, education, evaluation, and sharing of resources for composite design and manufacturing. CDM Hub provides a very powerful website called cdmhub.org for the composite community to carry out this mission together. We envision CDM Hub to become the premier resource for composite design and manufacturing in the near future. This webinar series is one of the initiatives CDM Hub started as a service to the community. This webinar series is made available by the support of CDM Hub sponsors, including Dassault Systems, SciTech Solvay, MAC Software, and Modex 3D. We greatly appreciate their financial support for CDM Hub. Next, I will show a brief commercial from one of our sponsors.
The Dassault Systems 3D Experience Education Center of Excellence in Advanced Composites is the result of a 7-year partnership between Purdue University and Dassault Systems. It is expected that this new level of engagement will bring significant benefits to the two partners and to the global society as we work together to bring the advantages of the digital age to society. Together, we will advance the digital enterprise by developing the human talent essential to this new paradigm and by utilizing the 3D Experience platform to exercise digital twins of complex composites manufacturing and performance to demonstrate the power for simulation of phenomena that are understood today only by empirical experiences. We will work together to introduce those concepts to a wide range of industries within the advanced composites community, from the original equipment manufacturers to the supply chain industries.
Thanks again for our sponsors' support. We invite more organizations to join them to serve the global composite community together. This webinar will be recorded and made available on CDM Hub. An email will be sent to you once the recorded video is available online. The presentation will last about 40 minutes and will have about 15 minutes for Q&A. All attendees are muted. Please submit your questions through the Q&A box. After the speaker's presentation, your questions will be read and answered. Next, I will ask Dr. Pipes to introduce our distinguished speaker today.
We're delighted to have Steve Arnold as our composites expert speaker today. Dr. Arnold is the technical lead for multiscale modeling within the Materials and Structures Division at NASA Glenn Research Center with over 30 years of experience. He's also the technical lead for Materials and Structures discipline within the Transformative Tools and Technology Project. Dr. Arnold conducts research involving theoretical and experimental investigations of structural material behavior of advanced composite propulsion systems and spacecraft structures. He's the author of Micromechanics of Composite Materials, a Generalized Multiscale Analysis Approach, published by Elsevier in 2013 and co-authored with Jacob Mabudi and Brett Bradnarchek. Dr. Arnold's research has produced over 100 archival publications and 2 patents. He's a member of NAFEM's Simulation Data Management Working Group, an ASM, Society of American Society of Materials International Fellow, active in the AIAA Materials Technology Committee, the ICME Working Group, and the Digital Engineering Integration Committee. He is co-founder and chairman of the Material Data Management Consortium. He has received the 2014 NASA Exceptional Technology Achievement Medal, the 2015 American Society for Composites Award in Composites, and the 2019 NASA Exceptional Service Medal. He is the co-founder and chairman of Material Data Management Consortium. We are delighted to welcome Dr. Arnold for his lecture today. Thank you.
Okay, thank you very much, Professor Pipes, for that introduction. And I just would like to also thank the organizers of this event for giving me the opportunity to speak with you today. To the audience, good morning, afternoon, evening, depending upon wherever you're located. I'm Steve Arnold, and I'll be briefing you on the various practical developments in multi-scale modeling of composites that NASA Glenn and its collaborators have made over the past few decades. The talk has been divided basically into 3 parts. I'm going to give a brief background, motivational information on why multi-scale modeling platform is needed for composites. We're going to do an overview of the IMAC toolset, and then I'm going to show numerous example problems demonstrating the practicality of the toolset. According to a 2016 multi-sector industrial survey, material innovation is essential to top performing organizations as they rated new materials as one of their most important factors in their ability to meet their innovation goals, particularly as you can see in the area of performance and cost. Yet, unfortunately, historical material development times required to move a material from conception to full deployment have been shown to be on the order of 20 years, regardless of the material class. Therefore, in recent years, there's been a desire to reduce this time frame dramatically in order to increase U.S. competitiveness. To that end, people have turned to ICME over the last 15 to 20 years in an attempt to speed up innovation, since ICME integrates processing histories which influence internal structure, which in turn drive properties, and then which drive performance of the component and structure. ICME is an approach to the design of products and the materials which comprise them by linking experimentally validated material models at different length scales. But multi-scale modeling is, it's an essential part of the ICME, but it's not really ICME. In that ICME requires iteration or optimization of the various scale-specific features to obtain one or more engineering performance metrics. Further, ICME attempts to marry 2 mutually exclusive viewpoints, non-mutually exclusive viewpoints or paradigms. The first is what I kind of term the traditional structural viewpoint, or the design with the material approach, where you're given a known properties of the material, and from that you design the component or structure, versus really a more science or material viewpoint, which is the design the material, approach, wherein given a specific performance requirements, a new material is designed that's fit for purpose. The handshake, between these two views is really the constitutive model, and the parameters and properties associated with the various materials influence then obviously the design of the components. And more recently, NASA has put together a 2040 vision, which espouses a public-private investment strategy for the design of fit-for-purpose materials and structures. This 2040 vision report is a community consensus document that addresses the technologies required to perform integrated multi-scale materials and structures modeling by the year 2040. The study engaged over 400 academic, industry, and government experts and aims to explicitly marry the design of materials with the design with materials approaches into one concurrent transformational digital paradigm. The document, which can be found at the URL indicated in the center of the slide here, describes a cyber physical social ecosystem that impacts the entire supply chain to accelerate concurrent design, deployment, and development and deployment of materials and systems throughout the product lifecycle for affordable, producible aerospace applications. Another large investment area in product development is in the area of testing. Consequently, the objective is to build a robust, validated computational framework that can provide accurate virtual testing in order to achieve significant cost savings throughout the development and certification process. Such a framework is particularly important when dealing with composite materials, as the amount of required testing at levels 1 through 4, as you can see here, are significantly increased. Notice 5x and 100x in levels 2 and 3 over those associated with metallic materials or structures. So to accomplish this, this speed up here, we really requires the development of a new model building block approach, consistent with the classical experimental building block approach. Thereby hopefully allowing us to minimize the amount of actual testing required during those intermediate stages of testing, that like levels 2 and 3, thus resulting in significant savings of both time and money. Here, as a result of these motivating factors and many others, NASA Glenn has been pursuing the development of robust composite multi-scale framework. And in particular, we've really focused, on looking at the differences between, or the balance between model efficiency and fidelity. And here I'm showing there's 3 different categories of multi-scale models. The first one here is hierarchical multi-scale approach, which is really uncoupled. It's one way. It's either bottoms up or top down. And typically it's very engineering oriented, where for engineering purposes we're more interested in efficiency and we assume a certain level of fidelity. Whereas alternatively, there's another approach is called the concurrent multi-scale approach, and this is where one in which it's fully coupled. All the scales are handled at once. And this is a much more of a science-oriented viewpoint, where again fidelity is more of the objective, and speed is taken to be a little bit less important. And then there's a third, which is what we have really focused on, and we've termed this the synergistic multi-scale, where we try to take the best of both worlds. And here we're doing fully coupled, but it's hierarchical in space and concurrent in time. And this is very applicable to the research and technology area. And here I'm just illustrating that in our opinion, GMC or the entire family of method of cells actually is very efficient, as well as has a significant level of fidelity, and serves our purpose. And so here I'm just showing here a snapshot of the evolution over 3 decades of our GRC multi-scale analysis framework. And the point I'm really just trying to make here is that, right from the outset, we started with MMCs, which are materials that involve or require handling of nonlinearity. And so we chose micromechanics that could deal with the nonlinearity. And then, as you see, we progressed and moved more into the PMC regime. And now in the last decade or so, we have been really focused on CMC materials. And that original material nonlinearity has really helped us out when we're trying to model CMCs, as you'll see. Just wanted to give a shout out to the various IMAC team members and collaborators over the years that have made what you're about to see possible. And I want to give a special thanks to Jacob and Brett, Evan, and Trent for their tireless efforts over the years. They've really done a great job. So let's just take a quick overview of the IMAC tool set. Here you're seeing the various scales that are associated with composite analysis. We start at the microscale, the mesoscale, and the global scale, and we're showing homogenization and localization, where homogenization takes you up the scales and localization takes you down. And we're indicating our 4 tool sets here. We have the MAC GMC standalone code, which involves classical lamination theory, and it also has a multiscale GMC kind of recursive algorithm built into it. HyperMac is the implementation of MAC within the commercial software code called Hypersizer, and FEA MAC and NASMAT, as I'll describe later, are the implementation of MAC within finite element framework. And clearly, we have, as I indicated, chosen the method of cells family of micromechanics theories to be the backbone of our multiscale framework. And here we're just showing that the nice thing about this theory is that we have macro level constitutive equations that are semi-analytical here, and micro level field equations as well that describe the local fields within the various constituents. And all of these are able to be obtained once we have the A and D strain concentration tensors. Furthermore, an advantage of like I indicated before, a generalized method of cells is that it admits nonlinear constitutive and damage models. And we have here, in this slide, just indicating that we've built in a large variety of constitutive models as well as damage models within our tool set. Just to give you a little taste of the theory, the generalized method of cells is a first-order Taylor series expansion of the displacement fields, and basically what we're doing is we're solving the continuity of displacements and tractions in an average sense along the subcell boundaries, here indicated by the blue X's, and then between the adjacent RUCs due to periodicity conditions at these points that are the orange diamonds. This formulation provides constant stress and strain fields in each subcell, and yet because of the discretization of subcells, we're able to pick up gradients within, let's say, the matrix or even the fiber. One of the advantages of GMC, though, is that it has no discretization sensitivity for a fixed RUC, but a disadvantage is that it also has no normal and shear coupling. Alternatively, the high fidelity generalized method of cells is based on a second order Taylor series expansion of the displacement field, which provides us with a linear stress strain representation per subcell, and actually allows now us to have normal shear coupling, which is really significant when you're dealing with disordered microstructures. A disadvantage, though, of this methodology is that, like finite element, you would have a discretization sensitivity within the RUC. For more information about the theory and the details that go into that, I recommend you take a look at our 2 books, Micromechanics of Composites, and our most recent book that will appear this summer called Practical Micromechanics of Composites. And also, just a note, this book is actually going to have a MATLAB open source code that complements it and provides access to Mori-Tanaka method of cells, generalized method of cells, and HFGMC, and it can be obtained at this link here, which is NASA's GitHub page. Okay, so and then just to give you a kind of a quick 30,000 foot view, the IMAX suite, as we said, there's a core a micromechanics capability. It's very modular. We have both GMC and HFGMC, as well as PHF GMC, which is a parametric formulation of GMC, CUF, Mori-Tanaka, and we can even allow any other micromechanics theory to be implemented. And then these, and this is done within a kind of a recursive algorithm. And each one of these micromechanics theories can pull from a library of constitutive models, repeating unit cells library, the property library, static failure analysis, interfacial debonding library of models, fiber breakage, and damage models. And we're continuing to include more modules all the time. And our most recent tool works on a high performance compute platform. The legacy tools now are like MacGMC. It basically just calls the generalized method of cells and the high fidelity generalized method of cells, but it can have loads applied, multi-axial loads applied at a given material point, or you can do micromechanics based laminate analysis with the Mac standalone. HyperMac is like I said, interfaces with the hypersizer code, and it basically calls just GMC or HFGMC as options. FEA Mac is our implementation, legacy implementation within Abacus that runs on a single CPU because FEA Mac was not thread safe. And our most recent and advanced tool set is NASMAT. And NASMAT actually can interface with any given third-party software through the macro API. We've so far connected it with Abacus, SPAF, and Calculic, which are other finite-only codes. And it has really the ability, which is quite unique, I think, and that is to recursively engage any given micromechanics theory at any level within the analysis. And you'll see some examples of this coming up. With respect to the tool set here, this just kind of lists the core capabilities of the tool and shows you our customer base. We've really had the good fortune of having, I think, a fairly large customer base that's used our code since 1995. 75 universities, 90 industrial companies, and 15 government labs have made use of it. And it is available free to U.S. citizens and organizations. Now let's move on to some examples to show you some of the benefits of the tool set. Here we're just going to mainly be illustrating the Mac standalone capabilities with respect to laminates and woven. Here, although all thermal-mechanical effective property components can be predicted, here we're only showing three, E2, G12, and Nu2 for two different PMC systems, a glass epoxy and a carbon epoxy system. Clearly here you see the results are shown for a Voigt, Roos, Mori-Tanaka method of cells and three different RUCs using GMC, and all do a pretty nice job. At least the method of cells and Mori-Tanaka and GMC match experiments quite nicely. Where of course Voigt and Roos are more on the bounds here. Okay, so let's touch on really the power of micromechanics, and that is that it provides access to the local stress states and stress and strain fields. Here I'm showing the two invariants, von Mises and pressure, and I'm showing finite element representation as well as GMC and HF. And then, of course, for simpler methods, mean field type methods like Mori-Tanaka, you only have a single value in the fiber and a single value for the matrix. But here you can see GMC and HF represent, the gradients and within the constituents quite nicely. And the point, getting back to this balancing of fidelity versus efficiency. Here you can see GMC is we kind of rank it very fast relative to finite element. HF is fast, and obviously the simpler methods are nearly instantaneous. But again, they only give you a single point value within each constituent. So now looking at the individual stress components, you kind of see the real difference between GMC and HF GMC, and that GMC simplifies things to where, in the transverse direction, this is a transversely loaded example, you see constant stresses along a given row or column within GMC because of the traction continuity conditions. And again, we're pointing out here that there's no induced shear stress due to that normal transverse loading. Whereas in FEA and HF GMC, you do actually see shear, but obviously the average of that shear is zero, and does agree with with GMC. So now with those local fields, we get to look at failure and obviously deformation and failure. And here I'm showing initial failure surfaces, which are margins of safety here, and I'm showing it for two different types of problems. Here's one is the 6-SIC BN system, where the yellow represents an interface material, the BN interface material, and here we're just showing a margin of safety curve. The green here doesn't have any interface. That is the yellow. Is material properties are the same as the green. Here, the blue shows what happens when you do include an interface, and yet you're not allowing it to actually fail. So obviously, it's providing you, because of the compliancy, it's providing you a smaller surface. But when you allow the interface to then fail, you're getting a very sharp, failure along that transverse direction. And it's significantly underneath. But one of the nice things here is you can see that not the different failure criterions in the different domains, and also we can pick up with micromechanics, obviously, because we have access to local fields, which phase is actually failing. Here it's the matrix, here would be the interface. And then now here on the right is a demonstration of the similar margins of safety curves, but here we're showing for three different surfaces, where the blue is a max stress criterion, the orange is a max strain, and the yellow is a psi-wu. And then the difference between the dotted and the solid lines are the difference in micromechanics theories, where the dotted are Mori-Tanaka and the solid is method of cells. And we actually have developed, full thermomechanical margins of safety as well. And now moving on, those were more initiation surfaces, obviously. And now, like here, we can have initiation, but we can also move beyond that and allow progressive damage to take place, where we allow each subcell to continue to damage, and then the accumulation of that damage ultimately results in, let's say here, the zero-ply failure of a quasi-isotropic laminate. One of the interesting things, as you kind of saw from the previous slide, there is a difference between failure theories when we're speaking about initiation, but when we get to the final failure and you've had propagation that goes on, the significance of the failure theory selected diminishes significantly. And then obviously, once we've done this now for an RUC, we can now actually take that RUC, plug it in at an integration point within the global finite element solution, and again have progressive damage take place now at the global scale, where the finite element is redistributing stresses throughout the structure based upon failure at the various integration element locations. And then the micromechanics is dealing with redistribution of stresses within the RUC due to damage at the various locations within the structure. And this is done iteratively until obviously you can predict component failure. Here's just an example again of a progressive failure analysis of a disordered PMC with MAC GMC, where on the left here we're showing the transverse tension of a glass epoxy system, or the mode 1 failure, and you can see the singular crack is able to be predicted. Here's a finite element, and the agreement's reasonably well between the two. And then on the right hand side is a transverse compression case, which is a mode 2 failure, and we're able to pick up the diverse cracking that takes place under that, and obviously depending upon the disorder of the microstructure, the values change. Here's another example of multiscale modeling of CMC behavior. Here we're showing two different types of problem. The first is a woven system. The second is a laminate. But we've done a significant amount of investigations of the stochastic nonlinear response of woven composites, where we've varied a variety of the different features at the local or lower length scales, and observed how they influence the behavior at the structural or up at the global composite level. And here we're just showing some illustrations where here the nice thing here, you can see the composite would go up, have failure, and then when you unload, you actually come back as one would expect at a different stiffness due to the fact that damage is present. Excuse me. And we're also showing here the in-plane modulus and the out-of-plane modulus, and you can see we're able to pick up the distinct difference between those two due to void pattern within the CMC, but also you can see that the evolution of and degradation of those modulus do take place, and they're different as strain is increased. And of course, then we can look at the probabilistic aspects of the stress strain curves and the properties as well. Okay, so and then in the with respect to laminates, we've done a significant amount of work on predicting the history-dependent response of laminated CMCs. Here we're showing the influence of processing histories and heat treatment on the subsequent tensile behavior of a CMC. And here we're taking actually into account 4 phases: the fiber, the matrix, the BN coating, and free silicon that resides within the silicon matrix. And the residual stress that results, you can see its influence here is to move up the initial failure, or what we call PLS of the composite, and that's at the sacrifice of the total strain to failure. And obviously, depending upon the type of heat treatment that is done, you can minimize or reduce, I should say, that effect of the residual stress due to manufacturing. Also, a little more sophisticated analysis involving fatigue. Here, we're just illustrating the implementation of a coupled deformation and damage methodology that's cyclic. I think the important aspect of the way we deal with it is we have 2 different types of failure. When it comes to a fiber, we reduce the strength of the fiber as a function of cycles, and we actually allow that strength to plateau and stop due to the saturation of interfacial effects on that degradation of the strength of the fiber. And then we also then do a stiffness reduction of the matrix, and combining these two, we're able to reasonably accurately predict the SN curve here for 090 laminate at temperature. And then even more interesting is that we can actually go in, and we've done that, looked at the effect of microstructure on fatigue curves. Here we're showing a 90, which obviously is the most severe effect of the microstructure under transverse loading. And we're showing that here we can calculate the full SN curve. But what's interesting to me here is at a given, any given load level, we're able to actually predict the distribution of the fatigue life. That's a function of various instances of the microstructure. So we've run 100 different instances here. The blue is coming from a 4 fiber RUC. The orange is from a 9, and the gray is 25 fiber RUC. And again, keeping with the spirit of understanding the difference between fidelity and speed and so forth, we've also thrown on here the analysis of the same load levels, but this is an ordered system with a hexagonal pack, and you see here that the hexagonal pack is actually, significantly faster, obviously, because it's only one calculation, but it matches the average of the 100 RUCs, reasonably well, and obviously it's also conservative. But it allows us to estimate life very reasonably, and we've also realized here that the hexagonal pack would be like a preferred analysis for multi-scale problems due to its efficiency over trying to deal with the stochastic nature and having to run hundreds or thousands of full multi-scale problems with different microstructures. And really tying in with this is this idea in the literature. A lot of most people have done studies with microstructure on a 90 laminate only. Here we're looking though that what the response is in a laminate situation. In particular, here is a 090, and you can see that the variation here is actually reduced quite significantly due to the presence of the zero ply, and in this case it's 62 times less variation in a 090 laminate. So that's something to really keep in mind from a practical standpoint, that more than likely if we have for at least laminates that are dominated by the zero ply, you're not going to have to worry too much about the microstructural details. Here's another example that we've done that's with respect to predicting woven carbon phenolic TPS material properties and being able to try to design a better composite for that environment. This is was a four level analysis. And what was interesting here is we actually used first principle results for the properties of the various constituents, and then looked at a fairly detailed RUC, and we were able to predict the modulus for both in plane and out of plane quite reasonably relative to the experiments over the full temperature range of 500 degrees here. And we're also able to predict the in-plane thermal conductivity and the through thickness conductivity as well. So moving on to now full integration within the FEA software. Here's just an example of an MMC that we did a number of years ago where we're looking at strength distributions. And here there's no strength distribution spatially. It's so that the strength is the same throughout the entire specimen. And clearly we missed the prediction with respect to experiment. But when we took into account the statistical variation of the fiber, in that we spatially varied the strengths of the fiber, we are able not only to hit the value or predict the value of the overall failure of the coupon, but the location of the failure was also able to be predicted quite nicely. And the lesson learned out of this was, when you start taking into account distributions, clearly you need to be careful and not impose symmetry boundary conditions or whatever, because that would bias your predictions significantly. And so next, here is just another example of a recent study that we were involved in. The Air Force had a Tech Scout study where they asked 7 different vendors or modelers to come and do blind predictions of 3 different layups. Here I'm only showing 2, layup 1 and layup 3, the quasi. One is hard, let's say, and one is a soft matrix. And overall, everybody did reasonably well. I think the overall blind predictions were within 20% for everyone, and the recalibration, which they allowed us to do, was 10%. Again, kind of the point of showing this slide is we're showing here 2D shell predictions as well as the 3D, which are in blue. And what was interesting to us is the fact that we characterized our parameters using MAC actually and lamination theory, and so it was interesting that the 2D shell was much more accurate than the 3D. And that just ties in with this idea of idealization, consistency, and the need for that. Also, we've had a variety of our users provide us feedback on their verification and validation activities. 2 notable ones here were Additive Manufacturing Innovation Company, where they were looking at tailoring the microstructure of turbine discs. And then GE, I think they probably have been the heaviest users of our code, and they told us about a 4-year AFRL study that they did, where they were able to successfully predict CMC smooth bar, open hole tension, and single edge notch specimen behavior using our tool set. And you might notice here, too, they were getting up into 600 million degrees of freedom problems, and obviously this would take a very long time on a single CPU, and this was one of the impetuses that we had for developing NASMAT. And NASMAT is our HPC multiscale analysis tool. It's a complete redesign of our tool set, or of our prior FEA MAC implementation. The memory is changed. The whole modular design has been changed, and it's much more plug and play. It has a lot more user functionality. It's better maintainability and upgradability, and of course, it's high performance. And with that, we had to make everything thread safe so that it could work within a high performance computing environment. Like I said earlier, it does allow us to have implementation of multiple micromechanics methods. So we're moving even beyond method of cells family. We've implemented Carrera unified formulation and the Mori Tanaka method as well. And I think one of its claims to fame here in the future is going to be this seamless handling of the multiscale recursive micromechanics, so that any of these micromechanics models can be called at any level of scale. Also, we're moving to these application program interface, which allows us to integrate with third-party micro and macro mechanics codes. And like I said, the real point of NASMAT is to give us the ability to do industrial scale problems. Here's an example of one of the things we've done with 3D woven PMCs more recently here, just illustrating now, 5 levels of scale, and where we've implemented or utilized crack band and sub-volume elimination methods to predict the progressive damage here of a 3D woven. And you can see they're both, quite accurate. Sub-volume significantly faster than this is on was done on one CPU, but it's 30 seconds versus the crack band model, which took 15 minutes. And you can see you're not losing much at all by using sub-volume over that of the crack band in this case. We've also done a lot of scaling performance studies to try to understand, how things are working and how do you and what differences it might make between having really discretized models at the global level versus more discretized or higher fidelity RUCs. And one of the interesting things I think that came out of that study was that the more complex the RUC is, actually the better we do in terms of matching ideal scaling. And we think that's probably due to the fact that we're loading the each CPU more uniformly. And then really too here we're showing that once we get above a certain global discretization, we're really not, it doesn't really cost us that much more to continue on and do additional elements. So that's kind of the end there of NASMAT. Now I'm going to go into kind of real quick here some insight into where we're heading in the future, and that is again with this idea of speed. We have started investigating machine learning, and here's an example where we've actually taken a multiscale model. That would be where, again, we're doing micromechanics-based laminate analysis, and we actually built a neural network that modeled that entire thing in one shot, and basically was able to represent the 5 points. In other words, 2 stress-strain pairs, one for the PLS, one for the UTS, and then the stiffness. So these 5 features were matched, and what we did is we ran tens of thousands of cases with MAC GMC for different constituent properties, different volume fractions, different laminate layups, and trained this neural network model to represent the physics-based model. And we showed ourselves actually that we could do this within 98% accuracy, but the speed was 10 to the 6 orders of magnitude faster, which was incredible. But this allowed us then to hook this up to an optimization algorithm, which involved the appropriate coordinate exchange algorithm and Monte Carlo sampling to give us the optimum experiment that would provide us with the knowledge about the hidden material properties with the least amount of uncertainty. And here we're showing you the heat maps for the conditional mutual information matrix. Here we're showing it for 3 different classes of composites, PMC, CMC, and MMC. And basically, what you're seeing is that the specific laminate layup that would give you that best result is different depending upon the system, as one might expect. But after doing this, then we decided, hey, let's go and actually model apply instead of the entire multiscale. And so we decided, and then obviously instead of just 5 points, we wanted to map the entire stress strain curve. And so Josh went off and developed a long short-term memory neural network model to represent MAC results. And again, after training and so forth, we were able to show ourselves that once again, we could accurately predict the response that corresponded to what we got from Mac, but at 145 times faster speed. So 2 orders of magnitude increase, where we embedded this surrogate model into a MATLAB lamination formulation. So again, this is very encouraging and very promising. So we're now in the process of working to implement this ML surrogate inside finite element. And finally, just as a final illustration, now think about the thousands of hours that it would take for us to compute fatigue life. So we're now in the process of developing a composite fatigue life estimation tool, so that in microseconds we can actually produce a stress strain or an SN curve for different laminates or for different microstructures or the combination of that, and provide a designer with an estimate of the fatigue life. So that's another project that we're currently working on. So in conclusion, I just wanted to say that efficient design with or the material can be obtained and is required for utilization of composites. Particularly in the case, when we want to understand the mechanisms of failure and so forth. And we do believe that IMAX Suite is an efficient and accurate nonlinear deformation damage framework for the design and analysis of composite materials and structures. And, for the following reasons. And a really nice one is this ability to do what if scenarios. And so we can better innovate and come up with better fit for purpose materials, and obviously this industrial size problems now, being able to do that is a really a big plus for us at this point. And then finally, integration of machine learning surrogate models we think are going to enable multi-scale modeling at industrial required speeds, yet with research level accuracy. So I'll just leave you again with this kind of pitch here for looking at the various books we've written, and I'll just highlight that the latest book coming out is really directed specifically towards students and practitioners, and as I said, it has a companion open source MATLAB source code that you'll be able to play with and I think really use to your advantage in solving and improving your intuition. So with that, I'll take questions. Thanks very much for your attention, and turn it over to the moderators.
Thank you very much, Dr. Arnold. I'll be happy to field questions here from the audience. Again, please enter your questions into the Q&A box, and we'll begin with a question about taking into account manufacturing variability and so on. Someone asked a question about how do these models take into account the variability that can arise from manufacturing, such as microstructure and so on that you've talked about, perhaps assembly, other kinds of variability in real life problems. How do you treat that, and how would you recommend others treat those problems?
Well, like I said, we have addressed those issues. We have built in, we have the ability to actually put in distributions of different properties, of different microstructures, and we very much explicitly account for the various features at the different length scales that they would be applicable to. One of the things that we've really found that's important, though, is to really think about at what level of scale should you be introducing those effects. Like, for instance, when I showed the strength, we by the way in which composites, at least the MMC was made, the variability of the strength is coming within the fiber, and so the strength needed to be varied spatially, and so we did that by binning different elements within a finite element model, and then giving each bin its own random strength within that distribution. So, I think it's pretty straightforward to take into account the manufacturing effects. Anything else?
Going more towards maybe certification, qualification by analysis, someone maybe following this thread asked the question, how do you assess the level of risk associated with that qualification by analysis such that it would be accepted by the airworthiness authorities?
Yeah, that's a really good question. And to be honest, I mean, we need to interact a lot more, I think, with the FAA and those types of people to really get a better understanding of how we would go about doing. We think the tool is there, and obviously you're going to have to make, like I said in that diagram of the testing programs, we need and we are trying to do assessment at each level and trying to understand how accurate we're able to predict the behavior at those different levels to try to assess that risk and validate that whole methodology. But that building block approach, that model building block approach, in my mind, is the way to do it. And I know industry collaborators are attempting to do that, and I know a number of them hold very close to their chest blind, you might say, validation tests to measure the quality of various methods. But that's a tough question, and one still to be determined, actually.
Thank you.
Anything else?
A couple of questions on machine learning, artificial intelligence, so on. One query about the amount of effort kind of behind the scenes to prepare and to run those models to get to the level that you're able to make the predictions you showed. And then a follow-up on that, someone asking, are there disadvantages of using the machine learning, and what would those be if there are disadvantages?
Well, first off, they're absolutely right. I mean, like for the fatigue, it's thousands of hours of computation, depending upon obviously the complexity of the RUC that you're going to be running, to be able to get the virtual data that you'll need to train the ML circuit, and how well your model does obviously depends upon how you're training. Now we're trying to minimize that training level, and our plans are to start to try to build in maybe some, like we'll say some of the physics into the machine learning algorithm, so as it can, it won't require as much training. But we're actually doing studies now and trying to learn how to perform those training exercises to try to minimize that computational time. Now, in terms of the disadvantages, I mean, obviously the way we've approached things is we're using our machine learning requires data. You don't usually have that much data. So what we're trying to do is we're trying to augment the actual data that we have with virtual data that comes from a formulation like Mac GMC. However, obviously the disadvantage is if you do that, the ML isn't going to be any better than Mac GMC. And if Mac GMC is missing certain mechanisms, then obviously the ML is going to miss it as well. But our approach is going to be that if we combine the virtual data with real data and in our training and so forth, we will be able to hopefully even make up for some of the deficiencies within Mac, because we will have captured those inherent mechanisms that we've not incorporated into the physics-based, and maybe through weighting the experiment more heavily than the virtual data, we'll actually be able to have a machine learning model that's actually better than the physics-based, and that would be great. But it's kind of too early to tell if we can do all that, but those are some of the things that we're thinking about and trying to take into account at this point.
Thank you. A couple of final questions just around clarifications I think people are asking. One being, if you might comment on the types of experiments necessary in order to use the Mac method, and another someone asking a question around the level of periodicity and how damage is dealt with when there is a level of periodicity?
Okay. Yeah, both of those are really good. The first one is, the type of tests are fairly straightforward. Obviously, we'd love to know the constituents. That's what we really need to know, right? And that's why we went off and tried to develop that optimal experimental design, because we have to, we often have to infer what those constituents are because we can't measure them directly, particularly like in CMC. So the question is, what are those global laminate level tests that you want to do that give you the richest amount of information? And so, traditionally somebody would think, 0, obviously a 90 ply, maybe a 0.90 ply plus minus 45. Those are the types of tests that we would take. And from those we would back out the in situ fiber and matrix. Now it's very important that you match your the theory each time. People I think mess up a lot when they take a given theory or take just pull constituent properties and don't think about the method and make sure that they've recalibrated those constituent properties for the given methods, because oftentimes you can't just take something that was characterized using method A and then use it in method B. Let's see, quickly, I'm trying to answer this. The second one, what was the second part of that question? It was
periodicity.
Yeah, periodicity. Yeah, and right, and obviously that can cause some real problems when you're dealing with damage, because the size of the RVE, in a sense, we're still trying to understand what constitutes an RVE or an RUC, in a sense, when damage is occurring, because obviously as that damage propagates, that RUC may actually have to become larger and larger, right? It all depends upon the size of the scales that you're dealing with and so forth. But that's an active area of research right now. We're still looking at that and trying to understand what is how's the best way to handle that in the context of damage. But that's why you see most of the studies we're doing are involving number of fibers within the RUC, how do you deal with the disordered aspects, all those kind of things. So because we're still learning how to actually use the tools that we've developed. Anything else?
Thank you. This has been a very, very enlightening hour. We appreciate you coming and sharing with us. To the audience, thank you for your participation and very good questions. And to everyone, we wish you a happy Easter, and thank you very much for coming here today. And we look forward to seeing you here on the upcoming webinars. Again, Dr. Arnold, our sincere thanks.
Okay, great. Thank you very much.